Hello. In this lecture, we're going to start out chapter 16. In chapter 16, we're going to be talking about energies of our electrons, looking at the electron itself. So this is our electronic structure of an atom chapter. So we're going to start out looking at um, learning objectives 1, 2, and 3 within lecture 14. So we're going to be looking at wavelength, frequency, our electromagnetic spectrum, and photons. Okay, so in this chapter, we are talking about the electronic structure of an atom. And when we see electronic, we should always think electrons. So we're looking at how our electrons behave within an atom. And generally, we think that electrons behave very similarly to light. So electrons behave similarly to light. So we're actually going to look at light first and then apply those same concepts to an electron. So light itself, light acts as both a wave and a particle. We call this the wave-particle duality of light. And electrons do as well. So electrons are going to behave the same way. So they can act both as a particle because they have mass, and they are going to be moving very, very quickly, and they're very, very small. So as a result, they're going to act as a wave. So has mass, small and fast. That's why it acts like a wave. Okay. So let's look at first our wave model of light. So light behaves as a wave. That's what most people really think about when they think about light, is behaving as a wave. Okay, so the properties are many of the properties, I guess I should say many of the properties of light are based on the fact that light behaves as a wave. So I would say that because it's a wave, it's a form of energy. And it is a form of energy in the form of a wave. So we would call this electromagnetic radiation. So energy in the form of waves is electromagnetic radiation. We have a whole spectrum called the electromagnetic spectrum, which is a spectrum of light. Or our waves, our energy waves. And it's going to start out very low frequency, um, which equates to low energy, and it's going to increase the frequency as we go up until we reach very high frequency waves, which are very high energy. So it is organized by frequency, which we give nu as our symbol for this. It's also organized by wavelength. So here we have this symbol, which is lambda, and also by energy. That uppercase E. So our radio frequency, so we go from radio waves to microwaves to infrared rays or waves to visible light, and then on to ultraviolet light, X-rays, and then lastly gamma rays. Our radio waves, lowest frequency, longest wavelength, smallest energy. And then our gamma rays are going to be the highest frequency, smallest wavelength or shortest wavelength, and then greatest energy. So our waves within our electromagnetic spectrum look like this, right? And we can have this kind of origin line here as reference. Let me rewrite this. Get our line. Whoop. Okay, so going from this point to this point, this is our wavelength. Okay, and then if we were to just take some arbitrary thing, we could count number of crests, which are these right here, or troughs, right here, that go through a certain point, go through that point in the course of a second. We call this our frequency. And it is a counted value over seconds. So it is given in per seconds, or seconds is -1, which is the same thing as hertz. So it's either per seconds or hertz. Now, if we think about the amount of crests or troughs that can go through at a certain point, the smaller that wavelength is, the more crests or troughs you can get through. So smaller wavelength is going to result in a greater frequency. And then again, if we think about our waves, so we have this type of wave versus this type of wave. This one has a longer wavelength, therefore it's going to have a smaller frequency. And compared to this one, it's going to have a lower energy. Looking at the other one, we can see it looks more energetic, right? It's because it has a shorter wavelength. So more crests or troughs can go through at a certain point. So it has a larger frequency and a greater energy. So we can relate these. If we look at wavelength versus frequency, we can see that they are inversely proportional to each other. They have an inverse relationship. As one goes up, the other one goes down. So we could show it simply as wavelength is proportional to 1 over frequency. And then if we look at wavelength versus energy, they're going to have a direct relationship. So frequency is directly proportional to energy. And then lastly, energy versus wavelength. The smaller the wavelength, the greater the energy. So our wavelength will be inversely proportional to 1 over energy. We can relate these again using actual equations. So our light is going to be moving at the speed of light. Technically only if it's in a vacuum, but close enough. So waves of light all move at the speed of light. So all of these right here, whether it's radio waves or gamma rays, these are all going to move at the same speed, which is 2.998 times 10 to the 8th meters over seconds. And since they all move at the same speed, we can relate the frequency and the wavelength using speed of light is equal to our wavelength times by our frequency. So a very simple equation to relate wavelength and frequency. We can also look at our wavelength and energy. Remember that they're going to have an inverse relationship. So here, our energy is equal to a proportionality constant times by the speed of light over our wavelength. So this proportionality constant we call this Planck's constant. And it has a value of 6.626 times 10 to the negative 34 joules times by seconds. And it's there to relate energy with our wavelength and our speed of light. So it has those joules in there, has the seconds to cancel all the additional units out. And then our last equation, so this is, sorry, wavelength and energy. Our next equation, we're going to look at frequency and energy. They are directly proportional. So we would say our energy is equal to our Planck's constant, our proportionality constant again, times by our frequency. Okay. Our wavelengths themselves, that's usually how we describe the energy of our waves, is through wavelength. And our wavelength is going to be given in a couple of different types of units. They're all going to be, with one exception, um, some manipulation on the meter, right? Because we're talking about a length. But if we're talking about things like X-rays or gamma rays, we're usually going to use angstroms to express those. If we're looking at ultraviolet or visible waves, we're using generally nanometers. Talking about infrared light, we're generally using micrometers. With microwaves, we're going to be either using millimeters or centimeters. Depend on where it is in that microwave region. If we are using radio waves, now we're getting waves that are very, very long. Here we're looking at meters or kilometers, so we can get incredibly long wavelengths in this spectrum. Okay, so let's try an example. So a photon is a packet of light with a set wavelength. We'll look a little bit more at photons in here, but we're going to have this photon, and we have a single blue photon. It has a wavelength of 464 nanometers. And we want to know what the energy of 1 mole of photons would be. So if we have 1 mole of blue photons, what is the energy of those? So the very first thing we want to do is we want to look at what we're given. The only real piece of information that we're given here is our wavelength. But we can use our wavelength and go from wavelength to energy using this equation. So in this equation, E equals hc lambda over lambda. We have h and c because they are constants, where h is 6.626 times 10 to the negative 34 joules times by seconds. Our speed of light, 2.998 times 10 to the 8th meters over seconds. And then we have our wavelength of 464 nanometers. And from here we can solve for our energy. Now, our units must be the same. If we look here, this is in meters, this is in nanometers. So we need to convert our nanometers into meters, remembering that 1 meter is equal to 1 times 10 to the 9 nanometers. When we multiply this out, we get a grand total of 4.64 times 10 to the negative 7 meters. Now we can put this into our energy equation. So energy is equal to Planck's constant, 6.626 times 10 to the negative 34 joules times by seconds, multiplied by our speed of light, 2.998 times 10 to the 8th meters over seconds, divided by our wavelength in meters, 4.64 times 10 to the negative 7 meters. So this will cancel out our meters, cancel out our seconds, and we'll be left with joules, which is what we want. So our energy here is equal to 4.26 times 10 to the negative 19 joules. But this is for one photon. So I would say joules per one photon. And every time I want to go from one particle, whatever that particle happens to be, into moles, I'm going to use Avogadro's number. So from particles to moles, I need Avogadro's. So we take our 4.26 times 10 to the negative 19 joules per photon. And then we're going to multiply that by Avogadro's number, 6.023 times 10 to the 23rd photons per mole. And we get a value of 2.58 times 10 to the 5 joules per mole. Good times. That is everything for this video. We will continue on into learning objective 4 in the next